of spatial computing that most people will recognize. But the applications and technologies have a reach much wider than these consumer applications. Spatial computing technologies have changed our society and infrastructure in profound ways. Spatial computing allows scientists and researchers to map the bottoms of the oceans and find the evidence of water on planets far away. Data scientists can quickly and easily create election maps in real time and air them on live news broadcasts to illustrate voting results. Epidemiologists can predict the spread of diseases such as the Zika virus, or track down the origins of foodborne illnesses such as salmonella, helping to prevent more people from becoming sick. Biologists can track endangered species to better understand their behavior and how they interact with their environments. Farmers use GPS and remote sensing in precision agriculture to increase crop yields while reducing costs. Protesters can form impromptu events via check-in models used by social media platforms. Google Earth is used in classrooms to teach children about their neighborhoods and the world in a fun, interactive way. A hiker in Yellowstone National Park, a schoolgirl in Washington, D.C., a drone over a Japanese rice farm, and an Uber driver in London know precisely where they are, what points of interest are nearby, and how to reach their destinations. All of these examples are part of an incredible historical shift in the way we access, create, and use maps, and the location technology that we explore in this book. 30 years ago, the majority of the world's population used paper maps for route planning. Most of our homes still contain these tools, now relics of different sizes and scales describing places near and far. A highway map to navigate across the state, a national road atlas to travel across the country, a local metropolitan map with an index of streets and their corresponding pages. But we have largely abandoned them in favor of digital devices. Today, roughly 2 billion GPS receivers are in use in smartphones, vehicles, and sensor networks, the so-called Internet of Things, with the ability to store all of that information and more, making it accessible at any time around the globe. We aren't just accessing location information, we are creating it as well. In our ride-sharing scenario, the driver and rider could not connect at the exact location of the original pickup request. Every moment a driver is not providing a ride means lost revenue for the driver. To minimize wait time as much as possible for both customers and drivers, the ride-sharing app takes the location input gathered from other points of connection and suggests them as pickup points for future ride requests. When the rider walked a block away from the event location, the driver and rider connected and created a new pickup point that was then reported to the ride-sharing app, adding information to the app's database, enriching the information for the app, drivers, and users. In addition to ride-sharing apps that are creating maps, dozens of apps on our smartphones are using our location and providing that information to app developers. Navigation and ride-sharing apps in the United States and around the world, such as Waze, Uber, Ola, and Didi Chuxing, estimate traffic speeds, choose less congested routes, and estimate arrival times at destinations from smartphone location traces. Our cell phone companies are constantly accessing our location using cellular technology, Wi-Fi, and Bluetooth, and analyzing those data to improve the accuracy of the information provided by the apps on our phones. Why spatial? So why do we call this technology spatial when all of these examples seem to refer to geographic locations? Although the most widely known and used applications of spatial computing work on the surface of Earth, new areas of this work expand its scope beyond geography and into